Okay, so the type of mechanism we're going to be exploring is called the SN1 mechanism. This is substitution nucleophilic unimolecular. And then we're going to go into the SN1 mechanism in much more detail in chapter 6, but I want you to understand the basic properties of it now. Here is an example. We're looking at tert-butyl chloride. That's the common name for it. It's also 2-methyl-2-propanol. This is the same reaction I showed previously. This is a tertiary alcohol. It's reaction with hydrogen chloride. So remember, tertiaries can react with HCl. Under some normal conditions, no heat, and we're going to make tert-butyl chloride, or 2-chloro-2-methylpropane, and water. The first step of this SN1 reaction is a proton transfer step. What happens is the HCl is going to donate a proton to the basic oxygen atom of an alcohol. When I say basic, I don't mean like it's a basic person, meaning that it is a Bronsted base in this instance. Now let's also think about this in the idea of Lewis acids and bases. I think that that is the better way to view this. So remember that a Lewis base donates electrons. So this is a Bronsted base because it's accepting a proton, but it's also donating electrons. So the oxygen donates electrons to the hydrogen here, making the hydrogen a Lewis acid. Okay, so they're both a Bronsted base and a Lewis base, and a Bronsted acid and a Lewis acid. The pKa on this, if you're talking about an acid-base reaction, because this is a type of acid-base reaction, confirm that this is a highly favorable process. We're doing this in conditions that are favorable, in very acidic conditions that are favorable to this alcohol picking up that hydrogen. And you can see what occurs is that the alcohol carbon now bears a more positive charge than previously. And we've now made a bond between the oxygen and the hydrogen. So again, the oxygen donated electrons. Usually when we have this donation of electrons, this is a formation of a bond. And you can see that this bond is breaking. See, the electrons are moving away from the bond and to the chlorine. So this bond is breaking. So again, we picked up the hydrogen, movement of electrons to form a bond here, movement of electrons to break a bond here. So we have a chlorine ion now. And we have this ion as well. This is an ion of the alcohol where the oxygen has a positive charge on it. So again, if we look at the energy diagram, here's our starting and here's our final. This is a transition state. The transition state is the point in which the hydrogen is moving. So it's broken off from the chlorine, but it hasn't yet bonded to our alcohol. And here is the final intermediate where we have that water group essentially attached to our alkyl group. Step 2 in this substitution reaction is called the dissociation step. So now that we have formed that ion, water is going to act as a leaving group and it's going to depart with a pair of electrons. See, again, our movement of electrons shows that this bond is going to break. It's going to give electrons to our positive oxygen and make water. It's also going to make a carbocation. This is an important word, carbocation. That's any type of hydrocarbon group that has a charge on it. So this has a positive charge, making it an ion, right? Ions are molecules that have full charges. And so this is a carbocation. Now this step in the reaction is the slow step. This is going to be the rate determining step. It's going to control the reaction in general. It's slow because the formation of the carbocation can be relatively unstable. So now that the alcohol carbon, the carbon that used to have the alcohol on it, has a full charge, what we're going to see is that it can act as an electrophile. And remember what we have around, it's not shown here, but in our last step, it's still there. There's still this chlorine atom around, this chlorine ion with a full-blown negative charge. So we have a carbocation with a positive charge and this chlorine ion around with a full negative charge. And water has now been removed. It is stable. Water is a stable molecule. But again, remember in this energy diagram, look at how big of an energy gap this is to form this product of the carbocation. This is a slow step. And again, it's because the stability of this carbocation can be relatively unstable, and that causes this step to be slow. Now, the last step is going to be what you might think. The negative chlorine is going to attack that positive cation. Remember, if we're going to use the words here, the chlorine is a nucleophile and the tert-butyl cation is an electrophile. Remember, electrophile means wants electrons. So where the electrons are going is the electrophile. It wants the electrons. Nucleophile wants to give electrons. So if we were to write if this is a Lewis acid or base as well, remember that our Lewis base is going to be, as we saw before, where you are donating electrons, and our Lewis acid is accepting electrons. So here, this would be, the nucleophile is our Lewis base, and the electrophile is our Lewis acid. This step is very fast because as you might imagine, as soon as you form that carbocation, it has a nice positive charge on it, positive and negative attract very quickly, and that chloride ion will quickly move to form a bond onto that carbon atom. And so you result with your alkyl halide. So now we have that same alkyl group, the same hydrocarbon group, but now attached, bonded in a full bond here with the chlorine. This is a very favorable reaction, and again, it's very fast. So if we look at the mechanism in total, again, you can see the start of the formation of our first step in which we're protonating is favorable. The energy is lower than the starting. However, the formation of our carbocation is non-favorable. The energy is much higher than either our transition or our starting. But then our very final product energy is the lowest and thus most stable of these set of products. Now the slow step in here is what we call unimolecular. I used that word earlier. Remember, this is called substitution nucleophilic unimolecular. that refers to the slow step here, in which there is only one molecule reacting at a time. So notice that in the slow step, we completely remove the water, so it goes away. The carbocation is by itself, and then we add the chlorine. Unimolecular, there's only one molecule acting on this carbocation at a time. And again, key thing here is that the stability of the product of the slow step is key. The carbocation stability is key to this reaction and how it will progress. So again, let's review what we know and what we talked about in these substitution reactions. We know that in an SN1 reaction, the rate determining step is the loss of the leaving group to form the carbocation. And we also talked about the reactivity order. So we know that, for example, if we started with a primary, secondary, or tertiary alcohol, the tertiary is most stable. And the reason for that is because a tertiary carbocation is the most stable form of carbocation. And so thus, a reaction with a tertiary alcohol will form a tertiary carbocation and will react faster. That's why tertiary alcohols react at lower temperatures and they do not require as aggressive as an acid. However, as you move down the line, if you start with a secondary alcohol, you'll form a secondary carbocation, which is a little bit less stable, and so the reaction takes longer. That's why these reactions need, for example, higher temperatures and a more aggressive acid. And that continues as you see. So the most stable carbocation is a tertiary carbocation. The reason for this is because alkyl groups are electron donating and they help to resonance stabilize the carbocation. So the more alkyl groups you have, the more carbons you have around. These are electron donating, and so they can stabilize this positive charge. Now, the less carbons you have around, the less they can stabilize the positive charge, the less likely you are to form a carbocation, and thus the less likely the reaction is to progress, or the slower the reaction is to progress. You can see how stabilizing extra carbons are in an electron density map. So if we look at electron density maps showing how alkyl groups disperse their positive charge. Now remember here, the positive charge in general is going to be located as a blue and negative is going to be as a red. And you can see that as we move towards the tertiary from the original methyl cation, we have a better dispersal of charges. Both the secondary and the tertiary, in fact, disperse their positive charge so well, and they have areas that are neutral or even some areas that are slightly negative. Again, resonance helps to stabilize them as well. So non-traditional resonance forms can show a hyperconjugation effect. Here is a carbon that is here is a carbon group on the side of a carbocation. And you can see that hydrogens can lose their electron, hydrogen bonds can lose their electrons to help stabilize in this double bond. Now, this is still the major contributor when we're not breaking the double bond. That's why it's a non-traditional resonance form. But its availability to do this, the more carbons are around, will help stabilize the molecule. Now, what we talked about in this transition state and talking about carbocation stability is described by Hammond's postulate. Hammond's postulate states that the transition state resembles the species to which it is closest in energy. So in the slow step of the SN1, the rate determining transition state resembles the carbocation. Structural factors that stabilize the carbocation will also stabilize the transition state and make the reaction faster. This part right here is the key in what we just said. So any structural factor that stabilizes the carbocation stabilizes the transition state, because the transition state, the part in which it's still kind of reacting, looks like the carbocation, which is what it will result in once the water leaves. And so by stabilizing this part of it, and we're more likely to make this faster. So more stable carbocations form rapidly than less stable carbocations. Again, a review of what we just said, and if you want to look at this in terms of an energy diagram, here's methanol. This is an alcohol that has no other carbons attached around it. And here's a tertiary alcohol going all the way to a tertiary alcohol. And you can see this is just showing that second step. This is the energy of the slow step. And as we go from methanol to a tertiary alcohol, that energy gap is much smaller. And so the reaction can proceed faster. It has less of a hump to get over to get to this transition state when it is a tertiary alcohol and more stabilized. Now, I said this before, but I want to give you a reminder that the reverse reaction of forming an alcohol from an alkyl halide also proceeds through an SN1 reaction. It just starts with different starting conditions. So again, here, instead of taking an alcohol and making an alkyl halide, you can start with an alkyl halide, but instead we're going to be reacting with water and some heat, and you can make an alcohol. And because this is an SN1 mechanism, because the carbocation transition state is the important state, it follows the same rules. It still follows that a tertiary reactant is more stable than a secondary or a primary. In fact, you don't even really see primary alkyl halides even being reacting through an SN1 mechanism to make an alcohol. So it follows the same rules that we just talked about. You just start with a different set of conditions that will make the reaction go from an alkyl halide to make an alcohol. Now, during this reaction, there are some key things that can occur in our post product. One happens to deal with chirality. So understanding chirality and its relation to a substitution reaction is very important because chirality is affected. When we look at secondary alcohols that are chiral, so if they have a chiral center and they're a secondary alcohol, it's likely that you will see an inversion of their configuration. So if they started as an S, as we see here we're starting with more S than R. We're doing a reaction with HCl and an alcohol, this secondary alcohol, remember. It's going to form 2-chlorobutane. And notice that now in our products, we have more R and less S. So we've done an inversion of the configuration from S to R, and any that were R are now S. So note that this isn't a perfect conversion. We don't end up with 84% S and or excuse me, 84% R and 16% S. Some retention of configuration does occur because the attack on the same face as because there's an attack on the same face as the departing leaving group. This is what that looks like. So when you form your carbocation on a secondary alcohol, and again, I'm going to key here that this is for secondary alcohols, the leaving group, although it has completely been removed, right, and our carbocation is technically open to being attacked from the chlorine from either side, meaning the chlorine could bond here or it can bond here. And depending on what side it goes to, it will either make an R or an S configuration. But if this water is taking its time leaving, that means that a chlorine coming in for attack on this side might have a little bit of a harder time than a chlorine coming in for attack on this side. So the side that was previously occupied, for example, if when bonded this was an S, if our chlorine attached on that same side, we would still have an S. If our chlorine attached on the opposite side, we now have an R. And because this water can sometimes be in the way, it's more likely that we do have this inversion, that it goes to the R side or to the opposite side in general. Now, again, it's still possible that you have some chlorine able to attack the face on the side, retaining its original conformation. Now, when you have a tertiary alcohol, you actually have scrambling. So in a tertiary alcohol, you get a racemic mixture, meaning a mixture of both the R and the S state. This is because tertiary cations are attacked with equal probability on both faces. So it's equally likely that in this case, the bromine can attack from this side or from this side, making a mixture of R and S. So the configuration of whatever you started with, whether it was R or S, is just scrambled. And again, this is for tertiary alcohols. So secondary alcohols, you have inversion. Generally, you have inversion. Tertiary alcohols, generally you have a complete mixture, 50-50. Now, for tertiary alcohols that have more than one chiral centers, if there is an equivalent face, a side that is more unstable, you will get an unequal mixture of diastereomers. So here we have two chiral centers. Here we have a chiral center here and a chiral center here. On this ring, the two faces of the carbocation are inequivalent. They are not the same. And that's because of this axial or equatorial position of the methyl. We talked about stability of a methyl group when it is axial with an opposing group. So in this case, it's actually more likely that we get the chlorine attack on the top side, going into the axial position here, and less likely that we get it in the equatorial position. And again, this is for a molecule that has more than one chiral center in which you have inequivalent faces, where one side is more sterically hindered than the other. Another thing that can happen in the substitution reaction is some unexpected products. So in some reactions of alcohols with alkyl or acid halides, you get unexpected products. So here we're looking at dimethyl 2-butanol. And what you would expect to be made, if everything's substituted correctly, is this, right? Our alcohol became a chlorine. But we don't see that. In fact, it seems that our carbon skeleton rearranged and the chlorine ends up bound at an unexpected site, right? Now it's here and it seems almost like one of these methyl groups is now here instead. So again, in particular, it looks like a methyl group has migrated. That is indeed what has happened. We're missing a CH3 group on this side, and now there's a CH3 group on this side. This is occurring due to some needed stability of the carbocation during this reaction. So shifts of hydrogen or methyl groups can occur in a carbocation when it improves the stability of the carbocation. So it involves a movement by only one carbon. So it can only be one carbon away for this to even occur. It can't be way down the line that we see a shift in carbons. And it leads to a more stable, more substituted or resonance stabilized carbocation. So here in our example we showed, remember we started with these 3 methyls on this side. Our alcohol was originally on this side, so we formed the carbocation on this carbon. This is a secondary carbocation, right? It has 1 carbon here and 1 carbon here attached to it. So secondary carbocation. If we were to shift a methyl from this side 1 over to our carbocation, as shown here, now we have a methyl group here and our charge has moved to the opposite side, over here. Now this charge is on a tertiary carbocation. Here's the carbon it is on, and that carbon is bound to 1, 2, 3 other carbons. So the methyl shift converted a secondary cation to a tertiary cation. So usually if you see a site that is a tertiary site next to a secondary site, this is a prime target for a rearrangement to occur of a methyl group. And again, remember, we can only move 1 carbon over. So it has to be a situation in which you have a tertiary next to it that has 1 carbon that's able to migrate. Methyl shifts from quaternary carbons are common because they result in carbocations. But tertiary carbocations also can result via something called a hydride shift. This can occur from tertiary carbons. So here again, we're starting with a reaction, 2-methyl-3-pentanol. Here's our alcohol. It's going to be protonated and leave, right? That's our first and second step. And you form a carbocation here. Now this is a secondary carbocation. It has 2 carbons attached to it. Now, instead of moving a methyl group over, we can move a hydrogen over. If this hydrogen is moved over to our position here, we swap the hydrogen and the positive charge. The positive charge ends up here, which is now on a tertiary carbocation, meaning it is now more stable. So notice a situation for this, which you're going to be looking for, is a situation in which you have this secondary alcohol next to a site that can become a tertiary alcohol when one hydrogen is moved over. Right, so same thing over here. This is where we have a secondary alcohol that is next to a site where if you move one methyl group, a methyl shift, it would form a tertiary carbocation. Or if you moved one hydrogen, it would form a tertiary carbocation. Now, these hydride shifts are more rare than the methyl shifts. Methyl shifts you see more often. But in general, whenever you see a secondary carbocation in a reaction mechanism, be on the lookout for the possibility of a rearrangement.